Indu, good morning.
Good morning, ma'am.
Okay.
This conference will now be recorded.
Good morning, ladies and gentlemen. It gives me an immense to cordially welcome you
Hello, Indu.
Hello,
Madam,
ma'am.
there is lot of disturbance, madam.
Yes, ma'am. One second, ma'am.
Ma'am, there is lot of disturbance.
Ma'am, shall I start now?
Ma'am, just a minute. There is lot of disturbance. We can start, ma'am, as the speaker has arrived.
Speaker has arrived, ma'am.
Okay. We can start, ma'am.
Good morning, ladies and gentlemen. It gives me an immense pleasure to cordially welcome you all to this wonderful webinar on automation and robotics. I request Dr. Nalini Joseph, Vice Principal and HOD of ECE Department, Lalala Institute of Technology, to give the welcome address. Over to you, ma'am.
Thank you, Ms. Sharmi. Good morning. This is Dr. Nalini Joseph, convener of this webinar from Laila Institute of Technology. It gives me immense pleasure to welcome you, all the participants from all over India, on behalf of our management, administrator, principal, and faculty members. I join together with our coordinators to welcome the speaker of today's session, our beloved alumni of our college from the batch of ECE 2007, Mr. Ashir Joshua, Senior Controls Engineer working in Barry Wehmeller Design Group USA, who have enriched experience in industrial automation and robotic systems. When I approached him first, he accepted immediately in spite of his time schedule, who is in America. He accepted for our convenience to conduct this webinar by 11 a.m. Thank you, Joshua. Really, you honored your teachers and the college. We are so proud of you. The day is yours. Welcome, Mr. Joshua. Definitely, there will be a lot of takeaway for the teaching fraternity and the student community in the field of automation and robotics from your speech. In this contest, I congratulate and appreciate the coordinators, faculty of EASY, and all our professional friends who made this possible. Really, this lockdown had enabled us to dive into the digital teaching techniques, and our now Department of EC has geared up to that DTT. Once again, I welcome our prestigious alumni, the speaker, and all the participants for this technical webinar. Happy learning. Thank you. Over to Sharmi ma'am.
Thank you, ma'am. As ma'am mentioned, the guest is very special, the alumni of a reputed institution, Mr. Asher Joshua. I request Mrs. Shanmuga Lakshmi, Assistant Professor, to introduce our speaker. Over to you, ma'am.
Thank you, ma'am. Good morning to all. It's my pleasure to introduce today's speaker, Mr. Ashir Joshua, who is a Senior Controls Engineer in Barry Wehmeller Design Group, USA. He is a skilled industrial automation specialist with 8 years of experience in design, development, and implementation of control systems for manufacturing plants and special purpose machinery. He also worked as automation engineer in Apaxis Industrial Automation. He enriched with knowledge in programming PLC, designing SCADA systems, motion controller programming, machine vision, multi-level industrial networking, control system solution development, and SQL. He worked for various projects such as automated mattress plant, downtime reporting system, foam encasement cell, mattress conveying system, automated glue insertion system, automation of detergent plant, and tablet packing machine. We are very happy to invite you for this webinar. Welcome you, sir. Over to Sharmi, ma'am.
Thank you, ma'am, for the brief introduction of our speaker. We use automation and robotics in our daily lives, but it's definitely different to hear it from a person who has hands-on experience on it. Mr. Asher Joshua will help us upgrade our knowledge in automation and robotics. I request Mr. Asher Joshua to take us through the journey. Over to you, sir.
Hello, all. A very pleasant good morning to you all. Hope you are all safe during this pandemic. Hope all your family is doing good. So I thank LIT for giving me an opportunity to share my knowledge with the student community. So I thank God for enabling all the. So I'm going to talk about industrial automation. So this agenda here for today. I'm going to talk about what is, and also I'm going to give some examples, application examples of industrial automation. it looks like someone has connected with the monks. Yeah, thank you so much. So and also I'm going to give you some example about some robots. So based on because of the very small time schedule, like I have just 1 hour, and I cannot go in depth. I'm just gonna show you what is automation, how we are automating machinery, and it'll be just like an industrial visit for you to walk into the industry and see how manufacturing is done. So, giving you a short example of what is industrial automation. So industrial automation is just like using a lot of control system. It might be either robots or PLC or computers or whatever it is to automate a process. So converting a manual process to like fully automated without any manual intervention, or with a little bit of manual intervention, like semi-automatic process. So this is called automation. So how is this automation done? The main thing to automate an equipment is a controller, a PLC. So we use a PLC, programmable logic controller here, to automate a process. So a very basic process can be automated without a PLC with just relays, but it'll be like very basic. But for any automated process, we need a PLC here. This is like the heart or the core of a control system. So what does a PLC do? The PLC gets information from the field. So it reads data from the field. Like we have like a lot of sensors connected in the field. It might be a proximity sensor, a photo eye, or whatever different inputs. So proximity and photo eye, I said, is a digital input. It might also be an analog input, which might be like temperature sensor or pressure sensor, or also it might be encoders to read the motor feedback. So whatever input it is, it's connected to the PLC, and PLC, inside the PLC, we have all the logic in there. And the PLC does all the processing, and it turns on the outputs. So it turns on the outputs. The outputs can be either a solenoid valve, if it is, or like motors or contactors, or there are like any type of output. It turns on the output. So this is what the PLC does. So now, well and good. We have the PLC in place. We are developing a control system. We have the PLC in place. We programmed everything, so everything is good to go. The machine is running good. So now, the programmers are there. Like after commissioning, is gone, and it's fully handed over to the maintenance mechanics there, or the manufacturing manufacturing team. They don't have any understanding of what's going on inside. So we should have a visual representation of what's going on inside. So that's why we have this HMI and SCADA. So HMI will be the one on the left side is an HMI. So it is just like a touch screen, or it's local to a mission. And one on the right side is like the SCADA system. It's like an overview process which shows the whole plant's information, like a very minute detailed information to a very overview information. So this is what is an HMI and a SCADA. So it shows you visual representation of what's going on inside the PLC, what is the status of the machine and everything. And also we can give input from the screen to the machine, like putting the machine to an auto mode, or a local mode, or remote mode, or like turning off some features, turning on some features. So all those kind of stuff can be done through this visual representation. So that's the HMI and SCADA here. So next, I'm gonna go into the manufacturing process. So in today's example, I'm taking an example of a mattress manufacturing plant. And in this plant, premium mattresses are manufactured. So when you say premium mattresses, the minimum cost of a mattress is will range anywhere between like 30,000 rupees, Indian rupees, to the very premium range of mattresses will cost around like 7 lakhs, 8 lakhs rupees. So it's like the premium brand. And what other thing is like, there is a lot of science also involved in this mattresses. Some mattresses may have foams which have like real diamond dust. Diamond dust has some properties to cool the body, a lot of stuff. So this is a background of what I'm going to show you, present to you today. So one of the process here I'm going to show you right now is a process in the plant where the layers are placed on a core. So what you see here over here is a core, and on the top here, you can see the operators placing here. So this process here is a fully manual process, completely manual process. So here you see a TV screen. This is a SCADA screen. So this SCADA screen gives a visual representation to the operator, like what layer to place. So what is the size of this mattress, and which pick location he has to go and fetch foam from. So this SCADA screen gives all the visual representation required for the operator. And here you can see some inputs. So here you can see a push button. Here you can see a push button. So these push buttons are input to the PLC. So based on this inputs, the PLC, does all the function. It takes all the inputs here, and based on the inputs, it drives the conveyors, drives the motors, and everything. So here we see the operator placing here, and he's pushing the button. You can see he's pushing the button, saying he has placed the mattress and his operation is done. Once the PLC receives the input, it conveys the mattress to the next conveyor, and it starts in feeding the next unit. Meanwhile, he goes to grab the other material required for this particular mattress, and he's going to place on this conveyor, and he is going to push the button once he's done. And this process is going to continue. So continue again and again. So if you see here, so this is a repetitive process. All he does is like he manually goes, places the foam, and brings it here. And here in this process, so once the layers are placed, the operator glues the mattresses, glues every individual layer, and then aligns it to the core, and make sure everything is all right. So this, just gluing one layer takes like 1 minute. So we are using here a hot melt gluing system for the bonding and a lot of ability. So since we are using hot melt gluing system, the open time is less. Once the glue is sprayed, the operator has to put the layer together in within 10 seconds. So here there is a lot of operator dependency for the quality of the mattress. The quality of the mattress is very much dependent on the operator. So let's see, we want to automate this process. So if we want to automate this process, we want to see what we are going to do. The first thing we want to do is we have to create a foam delivery system. And the next thing we have to do is create whatever control system we are creating. That control system should be able to handle this, very, very flexible material. That is the challenge here. And if we are going to put robots and all the other, automation, robots have very high accuracy. It's in millimeters. The repeatability of a robot, it's in 1 millimeter, 0.5 millimeter. It's 0.05 mm. That's the repeatability of a robot. So it exactly goes to the same location every time. So here, if we want to automate this process, the robot on the one side, on the other one hand, the robot has highly repeatability. On the other side, the foams we have, the raw material we have, is very, very flexible. Meaning, the tolerance of this foam is in plus or minus half inch. So it's 1 inch. There is a 1 inch play in the foam. So sometimes the foam might be oversized, sometimes the foam might be undersized. So we have to take all these things into consideration when we build a new control system. So let's see how we are doing here. The first thing, as I said, it's a firm delivery system. So you see on the top is an automated guided vehicle. We are going to use this automated guided vehicle to deliver our foam to the robot cell. So how does this automated guided vehicle work? Is, before going into the automated guided vehicle, what the process behind this operation here is on the TV screen over here. This is also another example of the SCADA screen. The SCADA screen shows you which layer to pick from and all this information, and also the corresponding on the left side. If you see the corresponding location, if you see here, whatever location this is, the corresponding location will show you with a light indication. There will be a pick-to-light system, so that particular location, the light will be on, so the operator doesn't make any mistake. He walks directly to the location where the light is on. He picks the foam and places on the AGV card. So this is the foam. This is the automated guided vehicle which was talking about. So this automated guided vehicle, it's like a wireless vehicle. So it connects to the control system, like to the PLC through Wi-Fi. It has its own server, and the server has an inside inbuilt OPC server, and then the PLC talks to the OPC server. This all communication happens through Wi-Fi. So if you see here, this vehicle here is connected to the Wi-Fi. And how does it, like if you see here, it just, like follows the yellow line. So under the yellow guard, under the yellow protective sheet, there is a magnetic strip. So a magnetic tape, so what the automated guided vehicle does is it follows the track. It follows the magnetic tape. So inside underneath, there is a steering and a magnetic reader. It reads, it can continuously reads the tape, and based on the magnetic readings on the sensor, it aligns and steers the vehicle towards, on the exactly over the tape, over the magnetic strip. Yeah, so I know all the tracking is done, and then the robot, the AGV,
என்ன காலையில உங்க எல்லாத்துக்கு முன்னாடி உங்களை என்ன தெரியுமா எப்ப நகை காசு பண்ணி
sorry. So the AGV, it follows along the magnetic strip, and it follows along the track. Now it's autonomous. It talks to the PLC through Wi-Fi, and everything is done. Everything is good to go. Then now, how does we know which location this cart is in? So that's why we have this RFID locations. If you see this is an RFID bullet, RFID radio frequency identification. We mount this on the left side. You can see it on the floor. So we put this on the floor, and then the vehicle will be having an RFID reader, and whenever it reads this particular RFID, it sends signal to the PLC, and the PLC will know where the automated guided vehicle is located, and based on that, it will give commands to the automated guided vehicle where to go next. So, and since this is fully wireless, this thing needs juice. It needs charge, right? So if you see here, this is the charging station for, yeah. So this is a charging station for this guided vehicle. So this is like a high-speed charger, just like how Tesla cars have supercharger. It's similar to that. This is like a DC charging, and it's like 60 amps. It has like in 5 seconds or 10 seconds, it charges from 50%, charged to 50%. So it's like a very high-speed charger. So that's how it goes around the loop, and meanwhile when the operator goes to pick the foam, it charges itself, and it goes to the next location. So that's how this vehicle works. So once it goes to the mission, it tells to the PLC, reports its location to the PLC, saying, "Hey, I've come here. I've reached this location, and the foam is ready." And what the PLC does, is it commands, all the control system inside the PLC worker. It comes, the delivery system comes in, it clamps using a pneumatic system, a pneumatic, clamp, and it drops it. So here, if you see, after it drops it, you can see multiple axes moving. So these are all digital outputs. All these valves are digital outputs, and based on you can see here. You see here the axis move. So this is the delivery system itself is axis. It's run by a servo motor. It's run by a servo motor, which means a servo motor will be always having a feedback. We'll be using absolute move or relative move based on logic. So, and these clamps, these are all digital outputs, just like just a solenoid valve. When we turn the air on or the valve on, the air comes in and it grips. When we turn it off, it opens. So it's basic, digital outputs. And if you see, the different axes, so you can see the axis over here a little clearly. So on the right side, you can see the axis. So these are all, like servo axes. These axes, align the foam. The foam might be different, every time the foam might be different, like the thickness of the foam will vary, the rigidity of the foam will vary. So based on the foam's thickness and everything, all the sequences are adjusted based on recipes. So here also the other thing is for different sizes, if it is a twin size mattress, it has to size differently. If it is a king size mattress, it has to size differently based on all the sizes. The whole mission works differently. So once it's aligned, it gives a command to the robot, and the robot comes, picks up the foam, and places it on the mattress. So I was talking to you about the open time, right? So here we have an automated gluing system. The gluing system, it sprays glue and everything. And here, if you see, the open time is very less. It's very controlled. There is no possibility of error. We've reduced, we are making sure the quality is good. It always aligns perfectly. We make sure, the quality and everything is very good. When we, when we design this process. And the other thing which I said was the tolerance of the foam. Sometimes the foam might be undersized, sometimes the foam might be oversized. So that's why we have this alignment table. Once the delivery system puts the foam to the alignment table, so what the alignment table does, it sizes the mattress. If it's like undersized, it stretches the mattress, and if it's oversized, it compresses the mattress. So now the AGV has come in position. It reports its position to the PLC. Once the AGV stops, it's going to clamp it, drops it. And once it drops, the foam, we don't know. The foam might be like oversized or undersized. So based on that, it aligns, it clamps, it stretches a little bit, and now it gives feedback to the robot, and robot picks the foam. So here, if you see here, so it picks over here right now, and based on the mattress size, you can see the end of arm tool. So this is the end of arm tool. The end part of the end mechanism of the robot is called end of arm tool. So even this, like you can see everything moving. There are like a lot of solenoid valves and everything, cylinders and everything. You can see these move based on the size of the mattress. So it comes over here, the size change. So now you saw. So based on the size of the mattress, you can see the end of arm tool adjusts itself to what is the next size of the mattress. So it comes here, places onto the layer. So you can see the layer going back and the mattress going back to glue again. So now it's going to get glued and it's going to come back, and once it's here, the next layer is going to be placed. So once the next layer is placed, it is going to be compressed, and it's going to be sent to the other cell. So here, here we have seen how we have automated a fully manual process into a fully automated process. So this fully automated process, improves the quality and improves the cycle time very much. So over there we saw the cycle time for one layer of one layer foam, one layer to glue one layer. It's what, 60 seconds, and here it's just 20 seconds. We have reduced the cycle time by 1/3, and what happens is, like, here we are increasing the volume, we are increasing the productivity of the cell. So this is what, like, automation does. Automation, like, improves productivity, which means improves efficiency, improves the volume, and also improves the quality. So this is the example of the this cell which I was talking about. This is called the foam encasement cell. So next thing I want to talk to you is another example is the foam encasement cell. What is foam encasement? We saw how the layers are placed on the, and we are going to see about how the foam encasement is made. If you see this, like this foam encasement. So what is a foam encasement? Is it will be having a base foam, foam on the base, and the rails, glued rails on the side, so that and then a core, like a core will be placed in between, inside the mattress, to build the core. So we are going to see how we have automated this foam encasement cell. We see here, this is an automated foam encasement cell, and here you can see a robot, like 3 robots working together. So there are 3 robots here which work in tandem, like it works together, and one of the robot is movable. So if you see 2 robots on the each side, this is stationary, but one robot it moves on the track. It has external axis. It has a track. So how this does, like this control system basically has 1 to 4 PLCs. 4 PLCs working together, like 2 cell controller PLCs and 1 area controller PLC. Like all these PLCs are working together. They talk to each other. They work together. And also, like there are 3 robot controllers. So these 3 robot controllers work together. There are multiple servo axes, 2 servo axes on each cell. Here for the movement of the table. So how this does is, like, every mattress has to be identified. So once the mattress comes into the cell, it will be read by an RFID reader, and the RFID reader will scan the mattress, read the tag, and send the information to the PLC. So the PLC will specifically know what particular mattress is being has come into the cell. What particular, you see over here, so there is a core coming in, and the robot is building a core bucket for this particular core. You see a core here. So the robot is building a bucket for this core, and then the core will be inserted into this bucket with a different machine. So it's like fully automated. So there's another machine which inserts the core into the bucket. So once we get the data, once the cell controller PLC gets the data, it queries the SQL server. It queries the MES system, which is the manufacturing execution system, saying, "Hey, I got this job. I got this particular job ID 1, 2, 3, 4, 5, 6. What do I do with this?" And then the SQL will return all the information required to build this mattress. If it is what size mattress that is, if it is a king, queen, king, whatever the size that is, and which pick location the robot has to go and pick from. So if you see here, like this is one pick location, this is pick location. The robot has to know which pick location it has to go and pick. So it goes to a particular pick location, picks the phone, and it has to wait for that particular robot which is picking the phone to be available to place the phone. So you see here, the main robot, the movable robot, which we call the base foam robot, it shares the same working space with two other robots. So here we need to be very, very careful when we program so that both the robots don't crash. So we have to have like a lot of interlocks together, and like both the robots have to be like talking to each other, and also the cell controller PLC should be like continuously monitoring both the robots so that they don't crash. They don't crash. So that is the very highly complicated thing when multiple robots are working on the same region. So the region is called what we call as a world zone. So right now, if you see, the robot went into the rail robots world zone, and it made sure like it was away from the world zone. So before right now you can see, so before this robot like goes to this zone, it'll check the status of the other robot, make sure it's not in its way and there is no collision, so that no collision is happening. So this is how Matters is built. Bucket is built. All the three robots we have here, all the three are exactly the same robots, exactly like same robots. And when I talk about robots, so the definition of robot itself will differ from an industry to an industry. So some industry, they consider robot only a humanoid robot as a robot, and they consider other as just a machine. And if we go for service sector industry, whatever they call robots is humanoids. And if you go to like different industry, many other industries like what even like the software industry, they call something as robot, right? So but those robots are just piece of code, piece of software which runs automatically or automates a software process. Even that, those are called robots. And even like in one way or the other, even a coffee machine is called a robot. So it depends on what what industry you are in and how you call what robot is. In the industrial automation, so if you are into industrial automation, if you're into control system, what we call a robot, we call a coffee machine as a mission. If it's a special purpose mission, so that can do just one job. It cannot do anything else. But a robot here is like a programmable machine. It's like a mission, but you can program it to any way you want. It's there will be a software for the mission, there will be a programming language for the mission, and you can program it any way you want. Yeah, you can customize it any way you want. So that is a robot when you talk about robotics in industrial automation. So so here you see on the robot is all the three here are exactly the same model robot, but it's doing different operation. The end of arm tool, which I which I told before, the end of arm fitting, the mechanical fixture, which which does the operation. So only that differs. So only the the arm of the end of arm tool differs, but the robot is 6700 series ABB robots, and it has a payload. It can take a payload up to 150 kilograms. And the reach is for 101 from the base, from the world zone origin. The reach is up to 1.5 meters. The reach sphere is 1.5 meters. So this is what. So here it's a perfect example of the same machine doing different jobs. So whatever we want to do, we can change the end of arm tooling to match our need, and we can automate the process, or we can make the machine to work in a specific process. So this is the example of a base form robot, which I said, and if you see here, I'm showing you how the matrix is built. The same here, it's exactly the same here as we talked about in the other cell. So the foam is not foam is a constantly varying object. So it's not an automobile industry. If it is an automobile industry, we are going to give the raw material for the robot is rigid parts, steel parts or metal parts, and it's always going to be the same. Here, there is a lot of variability. Even the supplier, the tolerance for the suppliers is, as I said, it's like quarter inch. So we need to consider all those things, and we need to make sure, like everything is good. We need to have the proper sensing mechanism for building, for our application here. So that's the care we need to take here. So this is it moves based on application. This robot, like it moves all along the track, and the cycle time is very less. In 45 seconds, bucket can be built. Whereas if you see a manual cell, we need two operators, and they need to take over a minute to build one bucket. So, and also the quality of the bucket is controlled here. Since it's all fully automated, the quality is controlled. So if there is a quality issue, they can always go and see what the quality issues and fix the quality issue. But when it is a manual process, it's not like that. A manual process, it's like fully dependent on the operators. So the operators can work good, or maybe most of the operators work good, but how they work will differ from a Monday morning to a Friday evening. So, but the robots can work every time the same way how it used to do. So here it's a very controlled environment, controlled process. But there, what we saw was in the manual process is a very uncontrolled process. It's dependent on the operators. So, and the next thing is we're going to see about the end of arm tooling. So here we see needle grippers. So this is what grips. So when the air is on, right now, when I shot this video, I turned off the air so that it's movable. But when the air is on, we use solenoid valves to engage or disengage the needle grippers. Once it so once it goes to a specific location, there is sensing mechanism. It goes to that particular location. It senses the foam, and then the robot says, "Hey, I've seen the foam," because every time the foam is taken from a pallet, the height of the foam is reduced. The height of the pallet is reduced. So we need proper sensing mechanism here to sense the robot. So we use here a photo sensor to see the foam stack. And once it reaches the foam stack, the robot stops its movement, and the needle grippers engage to grip the grip the foam, and that's what I see. So once it's engaged, it grips the foam and it lifts the foam. So once it's disengaged, when it's going to drop on the table, it disengages. So the needle grippers go back to its initial position, and when it goes back to the initial position, the foam drops on the table. So this is an example of a pneumatic system. Pneumatic system or pneumatic solenoid. This is a needle grippers. These are needle grippers, and this is the pneumatic system for grabbing the rail. So the same, the same like a pneumatic system. So once it senses the rail, it grips the rail. It grips the rail, and it goes to wherever it wants to place, and then it disengages so that it can place the rail. So here, this is a view from the other side, how it grips. So once it goes to the foam, it grips and holds the rail, which means the foam rail. So so here, if you see, this is I was talking about pneumatic system, right? So this is a cylinder. This is a this is an actuator. So if you see here, there are two pipelines. So one is an exhaust, and one is an infeed air. So this air we give highly compressed air of about 100 psi, and what it does is when we turn on the solenoid valve, the air flows in one direction, and this moves and it grips the foam. And when we want to turn it off, we turn off the solenoid valve, and the air flows in the other direction through the exhaust, and the gripper goes to the other home position. So this is, if you see, like all the all the grippers here. You can see this is the end of some tooling, so you can see all the grippers here. So they all work the same way. They all work the same way. So this is the, if you see here, this is the valve bank, what we call the valve bank. This is what manages air. So this needs a 24-volt digital signal. This is talking through field bus, through Ethernet IP. The purple cable here is Ethernet IP, and it talks through Ethernet IP to the robot controller, and so that it knows when it wants to turn this valve on. We have two valves here. So one is for the gripper and one is for the cylinder. So whenever this valve, when the robot gives a high signal, the signal comes through this Ethernet cable, and then it's being processed in this module, and it generates a 24-volt signal. The 24-volt signal triggers this solenoid valve. So the solenoid valve turns on and off this valve here. So turns on and off. So when changes the direction of air based on the direction of air. So underneath, if you see, so underneath are the plumbing which goes to all the grippers. So one is in-feed and one is out-feed. Based on the valve position, the airflow is changed, and then based on the airflow, the valve is either closed or open. So, and yeah, if you this is the in-feed, the blue and black. These are the in-feed and exhaust. These are the valve valves which control the flow of the air. And here, this is another example of how the plumbing is done. So here, if you see, this is another cylinder. So if you see here, you can see the cylinder move. So this is also the same thing. There's an in-feed air, out-feed air, and the cylinder, extends or retracts based on the command we give. So this is how we use. These are all outputs. Whatever I showed you just now are examples of outputs. So these outputs, it can be either the digital, pneumatic system, pneumatic valves, just like we saw here, or it might be servo motors or whatever it is. So what a controller does is gets all the information from the field, processes it, and drives all the outputs so that the process is automated. So one other thing I want to mention is, we saw all this, right? So it's not just programming how it should work. We should also program how it should not work. Just like in this case, it should not, the robot should not go into each other's zone, so that it has to work in its own zone. There are a lot of interlocks here, and when the robot places the foam, it has to work in a specific way. If the operator messes something, and if he has to abort it, there needs to be a recovery option. So there is it's not like thinking just one way about how it should work. We also think multiple ways. We need to see how the operators should not mess up the system. When we give options on the HMI, the operators should not be able to see everything on the PLC. We need to be very selective what the operators can see, what the engineers can see, what the maintenance technicians can see. We need to give different access levels to the operator so that they don't mess up the system. So that is one thing which I wanted to mention. Here, this is how we develop the programmer robot. So most of you will ask, how the robot runs, what language the robot uses. So here, in this example, we are using ABB robots. So for ABB robots, we use a software called Robot Studio, and we use a language called Rapid. The Rapid language is used only for the ABB program, ABB robot. It's so this was developed by the company ABB company, and so this is the simulation which we do before really putting everything in place. This is a simulation we do to make sure everything is running good. So here, what I'm what I'm going to do is I'm going to show you about the robot. So this robot is a 6-axis robot, and yeah. So this is a 6-axis robot, and it can move on the track. It can move. It's variable movable on the track, and I'm going to show you what this robot has, how many axes this robot has. So these are called links, and these are called joints. So to rigid, basically, like rigid objects are called links, and movable objects are called joints. So here it has 6 axes, which means 6 joints, 6 movable axes. So this is axis 1. So let me show you. Okay, I'm going to jog this joint. So this is axis 1 here, and this is axis 1, this is axis 2, this is axis 3, this is axis 4, this is axis 5, and this is axis 6. And why is it not okay? Okay, it's simulations, that's why. So now I think I should be able to jog it. Come on. Okay, so you see this movement is axis 1. If you see here, the axis is on, the motor is on the other side. You see the motor here. This is the axis 1 motor. It like drives it this way and that way. So you see here, this is axis 1 motor. This is axis 2 motor. So it drives, it can drive it either this way or this way. So this is one axis, and this is second axis number 2. This is axis number 3, which does this motion. This is axis number 4, which does this rotation motion. And this is axis number 5, which does this motion. So, and this is axis number 6, which does this motion. I'll show you. Okay. So, which does this motion. So basically, these are based with all these 6 axes has to work coordinatedly to go to a particular point, to a particular pose, so that it can do our operation. So here, let me go to jaw. Go to home. Okay. So this is the operation here. Okay. So now I'm going to show you the different degrees of freedom. So if you see here, this is forward and backward. The robot can move forward and backward. This is 1 degree of freedom. This is another degree, right, left. So it can move right and left. This is another degree of freedom. And the robot can move top and bottom. This is another degree of freedom. And also the robot can rotate along a different axis. So it can rotate along the x-axis. If you see here, see here. So the red thing is the x-axis, the green is a y-axis, and blue is a z-axis. So here it can, rotate along the x-axis. It can rotate along the y-axis. Yeah. So it can rotate along the y-axis. If you see here, all these 6 axes are working together. So axis number, you can see axis number 1, axis number 2, 3, 4, 5. All the axes are working together to make this movement. And so this is this is number 5, right? So, and the last movement is this is 1. This is 2. This is 3. So basically, this robot has 6 degrees of freedom. 1 is forward, backward, right, left, up, down, and also it can, move along, it can rotate along the x-axis, it can rotate along the y-axis, it can rotate along the z-axis. So it has 6 degrees of freedom. But for our application, we are not going to use all the 6 degrees of freedom. We are going to use the forward, backward, right, left, top, down. So that's 3 degrees of freedom, and we are going to use just this degree. So it has to rotate along the z-axis. For our application, we are not going to use this rotation or this rotation. So throughout, throughout this simulation, if you see, you'll be seeing only the 4 degrees of freedom operating. You'll not see the other 2 degrees of freedom working. So I'm just going to simulate the pick sequence here. So let me go to okay, so now I'm commanding it to go to the home position. So it recovers and goes to the home position here. So now it's going to pick. So once it goes to pick, okay, so it's dropping the foam right now. So I'm resetting the cycle. So now it's in home position, it's ready to run. I'm commanding it to pick from location 5, which is this pallet over here, all the way over there. So I'm commanding the robot to pick it from location 5. And these are the sensor signals I'm going to simulate. So let me run it. It's going to pick from location number 5. So you can see it's rotating, the end of arm tool rotating, and it's going to come here. And I'm simulating one signal, I'm simulating a second signal. Okay, now it's picked. Now it's picking up, and it's going to the home position. It's going to go to the home position. And now I want to drop it on the other table. So I'm calling the drop rotation. So it's going to drop it to the other location. So here, so this is the simulation, with the front end simulation which we are seeing. So how is this running? What is the backend code? If you see the backend code, so this is the backend code which is running. So this is the different work objects for different pallets, and all the code here. It's it's not that complicated. It's simple code if you know basic programming like C, C++ or something like that, you should be able to easily read this code. And it's a test case. It's what it's a while loop, test case. Simple code. Some of the features you might not be able to understand. It's specific to robot programming language, but most of the syntax and everything, it's all similar to C or C++. So this is the coding behind this robot. This is how this particular specific robot runs. And coming back to our presentation, and because of this pandemic situation here, the APP has given free licenses until 2020, the end of 2020. So we have 5 more years. So you'll be able to go to the ABB website and download the software. There are a lot of documentation for learn robotics, and also a lot of tutorials on the YouTube. You can see how we can just start up how you want to program. The cost of this robotic programming software, the studio software, is very high. It's the minimum with no options. It comes to $1,500. It's more than $1 lakh for 1 year. So that's how much with all the added functions, it goes to up to 3 or 4 lakhs. So that much costly software, the company is free until 2020. So I encourage all of you to go to their website, download the software, install it. If you are interested, if you're really interested, this can be a starting point for you. You can simulate different robots and see how things are done over here. And that's it. So I've given you a basic overview of what is industrial automation and what is robotics, and it's like a high-level explanation, high-level talk of what's going on in the industry, and to see how things are done. And I'm open to questions.
Marvelous presentation. Thank you, sir. It definitely was like an industrial visit. Being in academics field, it is very interesting to know how the industry works. We must thank you for sharing your precious time and knowledge with us. Now it's time for queries. We already have a lot of questions in the GoToMeeting and YouTube chat box. The GoToMeeting chat box questions will be presented to you by Mrs. Priyadashini, Assistant Professor, ECE Department. Over to you, ma'am.
Thank you, ma'am. It was a marvelous presentation, sir. Thank you. Many participants are actively posting their queries in GoToMeet chat box, and I have picked up few questions for you to answer. And the first question is from Ms. Divija. And the question is, can we use this automation technology in our Indian space defense mechanisms and space research? If so, how it can be used?
So there is, automation. There is no limits for automation. You can also use automation in your kitchen. So automation doesn't have any constraints. It can be used anywhere. For your question about the space in the space domain, there is already automation available in the space domain. So if you see the space shuttle, right? I think most of you have known about the space shuttle. The space shuttle has a robotic arm. So that robotic arm was, even though the space shuttle was built and designed by USA, just the robotic arm was built by Canada, by a company in Canada. So in those days when the shuttle was designed, there was not that much robotics company in the USA. So they reached out to Canada, and Canada they built this robotic arm. So if you can Google about the robotic arm in the space shuttle, so that will be an explanation for you for your question. So yes, definitely there is a lot of opportunities in space, and even currently they're using robotics in space.
Thank you, sir. That was a nice answer. And the next question is from Mr. Kiran Prakash Rao. And the question is, what is the impact of automation on employment? Will it get increase or decrease?
So this is a nice question. So every every automation engineer gets this question. So if you see, as far as in my career, what I've seen is it doesn't take away people's job. What it does, it might in some cases, but what it does is, it switches it improves the productivity. For example, in a plant, without automation, if they are manufacturing or whatever it is, if they're manufacturing some 1,000 units, 1,000 pieces a day, or 1,000 products a day, with automation, with all automation, we can improve the capability of the plant. We can improve the capacity of the plant so that they can make 5,000 products a day or 3,000 products a day. We are increasing the capability of the plant. And the next thing is now the operators are, instead of doing everything manually, they're going to operate machines. They're going to operate missions, and they're going to operate, they're going to feed the missions. So they're going to feed raw material to the mission. The role of job will be changed. I don't think automation is a threat to employment. I think automation is the way to go, because, how does an operator get job? Only if the plant, how does the the operators or the, employees get paid? Only if the plant is sustainable, if the plant is profitable, if the plant can produce a lot of units, manufacture a lot of units, if the plant is productive, and also if they can make quality products. Think about an example where a plant makes like 1,000 products a day, and out of the 1,400 products return because of quality issues. That's a big thing, right? So this automation checks the quality of the product, and also it checks the, it increases the productivity of the plant. So I greatly think, this is the way to go, and this is the future.
Thank you, sir. Thank you for the elaborate answer. And the next question is from Ms. C. Harshavardhini. And the question is contribution of nano robotics in biomedical equipments. If so, tell some of the process.
So this is a specific question to bio technology, I guess. So I think there are a lot of robots which are assisting lab assistants, or like for doing various tests. A lot of machineries, doing the test for the culture and everything. This is very specific to the biochemistry, or like that department, which I cannot answer. But there is a lot of robots in the industry.
Thank you, sir. And the next question is from Mr. Bhargav Padya. And what is automatic guided machines efficiency?
Hello.
Hello, sir. Can you hear me? So, from Mr.
Sorry,
Bhargav.
Yeah, sorry, I missed you there. Yeah.
Okay, so what is automatic guided machines efficiency?
So, automated guided vehicle. So, you said automated guided machines. I don't know if you're talking about automated guided vehicle or the automated machinery, or the special purpose machinery which we saw. So I'll just explain both in whatever case you asked. So efficiency, what is an efficiency of an automated guided vehicle, or efficiency overall for a mission is, it is measured by the availability of a mission, which means the mission should be always available. There should not be any downtime. The mission should be in a good running condition. So that's that's how the efficiency is measured. So always a mission should be, for example, we'll consider a mission. So if that mission is available for 24 hours a day, which means it never broke down on the day, there were no issues with the machine, there were no hardware issues, there were no software issues, it was always available to run the whole day, 24 hours a day. And then if it was always fed with the product, so the in-feed was always, whenever you say, hey, I'm ready to process unit, oh, okay, so there is a product, there is a raw material to process, to work on the machine. And also, whenever the work is done, the outsheet should be always ready to receive the completed unit. So basically, the machine should be always available without any downtime, any issues. The machine should be always available at the in-feed and at the outfeed of the machine, and it should always produce 100% quality products. So if these three are always 100%, then that machine is running at 100% efficiency. So if any one of this is like a little bit low, the machine broke down like for 10 minutes a day, or if the in-feed was empty, or if it was waiting for an in-feed, waiting for a product to process, so the efficiency will decrease. If the outfeed is blocked, if the machine can work good, but if the outfeed is blocked and if it cannot send out processed units, then the efficiency will decrease. Also, if the machine is producing, there are any quality issues with the product which is made, then that will also decrease the efficiency of the product. So based on all this, that's how the efficiency is calculated. It varies on different mission, different situation, different different products, different plants, different process. So this we cannot specifically say this is the efficiency of this mission, this is the efficiency of this mission. It also depends upon the process, it depends upon the product, so there is a lot of variability here. So that's how the efficiency is calculated.
Thank you, sir. Thank you for such a brief answer. And thank you for your patience in answering the questions. Next, Mrs. Pavitra, Assistant Professor of ECE, will read out the questions from YouTube chat box. Over to you, ma'am.
Thank you, ma'am. Thank you, sir. You have just delivered as an outstanding presentation. Participants are asking queries in YouTube live stream also. So I have picked a few questions for you to answer. First question is from Mr. S. Ramamurthy, sorry, Dr. S. Ramamurthy. It is about a dimension automation. What is the maximum number of dimension the automation can be implemented?
It's 3 dimensions, so X, Y, Z. So it's basically, when you consider a robot, it's, there are single axis robot, which can move in only one axis. It can move either forward or back, right or left. Now there are single axis robots. There are, 2-dimensional robots. The case of the air table, which I showed you, it was able to go in x-axis and y-axis, but it was not able to go in the z-axis, right? So that's 2-dimensional automation. So it should be able to go in the x-axis and it should be able to go in the y-axis. That's 2-dimensional. And our robot, which I showed you at the last, that's an example of 3-dimensional motions. So what the 3-dimensional motion, how the robot works in 3-dimension is we'll specifically specify a point in space. So from the base of the robot, which is the base reference frame, from the base reference frame, this particular point is located this much mm in the x-axis, this much mm in the y-axis, this much mm on the z-axis. So we'll give all the coordinates and also which orientation each axis, each robot axis, all the 6 robot axes should be, which orientation the robot should be there. Based on that, we ask the robot, okay, so go to this point number 1. Point number 1 is x1, x2, x3 with the orientation r1, r2, r3. Go to this point, and then the robot goes to that point and say, hey, I've reached the point. And then after it's gone there, I'm saying, okay, so now turn right this much degrees and go up, go left. So that's, it's just a 3-dimensional point in space. And we use those points to program the robots if it is a 3-dimensional mission. If it's a 2-dimensional mission, we just give the XY coordinates for a mission to move. And if it's a single-dimensional mission, we just give the X coordinates.
That was an elaborate answer. Thank you, sir, for answering. Next question is from Ms. Jyoti Patel. What is accuracy and consistency of robots maintaining? How maintenance of the robots can be done?
So maintenance, it's not only the robots, all the machines, all automation equipment, all mechanical equipment has to be maintained. There should be preventive maintenance. The manufacturer will give you a specific example. For example, in the case of our robot, which I saw, the track robot, it goes at a high speed, to and fro. For example, if it for one particular mattress, for making one mattress, it has to go forward once and it has to travel the same distance backward once, right? So if the plant is making 1,000 units a day, if the plant is making 1,000 units a day, then the robot has to go forward 1,000 times, backward 1,000 times, which is 2,000 times, right? So for a week, it's on an average, it's 10,000 times, and for a month, it's 30,000 times, and for a year, it's 30,000 into 6, 360,000 times. So, for in 2 or 3 years, if you see, the robot would have cycled 1,000,000 times, right? So that's a huge number. There will be a lot of mechanical constraints. There will be a lot of wear and tear. The gearbox needs to be, every axis has a gearbox. So the gearbox has to be serviced. It has to be serviced properly. The oil has to be changed. The maintenance has to be done on a regular basis. So how on the plants they do is they schedule maintenance. So they schedule maintenance. Okay, so for this month, we are going to do maintenance of this robot on the weekends and when the plant is not running, and then on the next week they'll be on the next month they'll be working on other robot. So it's any mission should not be down when the production is running. That's very, very important. So if a machine is idle, the plant is losing money. The plant cannot make products and it's losing money. So the productivity of the plant has to be high. The machine uptime should be very, very high. For that, preventive maintenance should be done regularly for all the machines.
Thank you for answering the question. And one more question is from Vineet Shrivas. What is mean by degree of freedom of robot, and how many degree of freedom the robot has?
So it depends on. So degree of freedom is how many orientations are, like how many different ways the robot can move. So in the simulation which I showed you, so we saw the robot. It was able to move forward, backward. That's 1 degree of freedom. Right, left. That's another degree. And top, bottom. It can go up and down. So that's 3rd degree of freedom. And so it was not only able to do linear movements of x-axis towards x-axis, y-axis, z-axis. It was also able to rotate along the x, y, and z-axis. So rotating along the x-axis, that's 1 degree of freedom. Rotating along the y-axis, that's 2nd degree of freedom. Rotating along the z-axis is the 3rd degree of freedom. So totally, the robot which I showed you in our example, that particular robot has 6 axes of freedom. It depends on every machine, every robot, like how many degrees of freedom we need, how many degrees of freedom the machine. It all depends upon what machine that is. But in our application, we saw 6 degrees of freedom.
Okay, sir. I think the question was answered. And one final question. Some of the participants are asking about the working of the DC charger. You have shown in your PPT, I suppose, right?
Yeah, so that's so most of you might have known about the Tesla cars, right? So for Tesla cars, it's like an electric car, and there are like superchargers, Tesla superchargers. How it does, once it's plugged up, once the car is plugged in, high current, like the charging, very quick charging is possible through that Tesla charger. It's the similar concept here. So usually, like all the industrial systems, whatever industrial system you take, it's the industrial system will be having 24 volts. So that's what it might be a sensor, or it might be the PLC, or most common voltage, DC voltage, which all the components work, all the electronics work is with 24 volt DC voltage. Even the same thing here. That particular automated guided vehicle, which I was showing you, was it has there is a charger there in the floor. There was a positive and negative terminal, a copper strip on the floor. So what happens is the cart goes to that particular location, goes to the charging point, and it reports to the server saying, "Hey, I've reached the charging location." Once it gets to the charging location, then what the server does is it will turn on the charger so that it injects high current. The drive system will be there will be like power converters and everything specifically designed for that application. So it should be able to do a quick charge, like in 10 seconds or 15 seconds. It will be able to charge the vehicle from 0% to like how much ever it needs. So that's the DC quick charge feature.
Thank you, sir. That was an elaborate answer. And it was a wonderful session. As Sharmi ma'am told, it was like an industrial visit, really. And thank you for giving us such a wonderful webinar. Thank you, sir. Over to Sharmi ma'am.
Thank you, ma'am. Most of the questions in the chat box has been addressed, sir. All the remaining questions are noted. and will be sent to you through mail. Dear participants, we have posted a feedback form in the GoToMeeting and YouTube chat box. Kindly fill all the details and send to us. You will receive your e-certificates within 2 days. If you find any difficulties in the feedback link, it may be due to the condition in the server. So wait for a few minutes and try again. Thank you. Now we have come to the session. I request Ms. Stefina, Assistant Professor, ECE Department, to deliver the vote of thanks. Over to you, ma'am.
Thank you, ma'am. I deem it a great honor to propose the vote of thanks to all who have helped us in making this webinar such a resounding success. First of all, I would like to propose a hearty vote of thanks to our speaker, Mr. Asher Joshua, for gracing your important work in spite of your hectic time and work schedule. Thank you for updating our knowledge on PLC, SCADA, and the softwares used, and also an in-depth knowledge on the mattress manufacturing plant, and help us to learn us about the various mechanisms. Thank you, sir, so much for your excellent presentation. It was very lively. I would also like to express a profound gratitude to our management, administrator, our principal, for giving us the opportunity to host this webinar. I thank our vice principal, our convener, Dr. Nalini Joseph, for making this webinar the right path for the success of this webinar. I thank the coordinators and the faculty members of EC department for your extended support. I also thank all the participants for your kind cooperation throughout the session. Thank you one and all. Over to Shami, ma'am.
Thank you, ma'am. All the participants, kindly fill the feedback form. You can leave the meeting one by one. Your e-certificates will be sent within 2 days. Thank you all for your participation and patience.
Joshua, really heartfelt thanks, Joshua. On behalf of all the participants and behalf of all the teachers of Laila Institute, we really thank you, Joshua. ரியலி சங்கர் படம் பார்த்த மாதிரி இருந்ததுன்னு வச்சுக்கோங்களேன். எங்களுக்கு ரியலி இண்டஸ்ட்ரியல் விசிட்டடா மேல இது அது எங்க குழந்தை சொல்றப்ப எங்களுக்கு எவ்வளவு சந்தோஷமா இருக்கு. when our student says it is like open house, taking the parents and relatives in கூட்டிட்டு போய் காட்டின மாதிரி இருந்தது. So really tears are rolling in my eyes. So you people are reaching the heights, and we want our present generation students also inspired by your talk, the way you motivated them, the way you guided them with the ABB software எல்லாம் ஃப்ரீயா கிடைக்குதுன்னு சொல்லியிருக்கீங்க. So the present day students should make use of this, and really our faculty will inform through various groups to make use of this ABB software to acquire a knowledge or about a skill set in robotics as well as automation. And anyone approach you also, please help them. Really thank you, Joshua. We didn't expect this much of presentation from your side. ரொம்ப நல்லா இருந்தது பிரசன்டேஷன். என்ன கேட்டா தாயின்ற மாதிரி
You're welcome, ma'am. It's a honor to me.
Really நிறைய மெக்கானிக்கல் டிசி ஸ்டூடண்ட்ஸ் நிறைய வந்திருந்தாங்க. ரியலி இஸ் a great. நல்லா இருந்தது பிரசன்டேஷன். பேசிக்கிட்டே இருக்கேன் போல இருக்கு. Thanks a lot, Joshua.
It's really a pleasure to me and honor to me, and I also thank God and also thank LIT for giving me an opportunity to share my knowledge with the teaching. Thanks all.
Thank you, Joshua. Yeah, thank you. I think it's time for you to go to bed. It's very late. Thank you, ma'am.
No problem.
I'll call you. Thank you. Good night, Joshua. Thank you, participants, for your patient listening. Hope you all have a lot of takeaways and a lot of inspiration from our beloved alumni. Thank you. Thank you all.
Dear participants, kindly fill the feedback form and leave the meeting. You will receive your e-certificates within 2 days. Thank you.